Powerus are some of the best amplifiers on the market right now. However, not everything is immune from developing faults. This one has a problem powering up. It's glitching around, the fans are spinning crazy, and it won't come out of protect. There are no dead MOSFETs here in the power supply or in the output section, and occasionally it does power up fully, giving us output class D switching, however only generally at a lower input voltage around 9 to 10 volts. As soon as we go up to 12 volts, it doesn't really come on for very long. The first thing to do is see what's on the power supply MOSFET drain, and it's kind of glitching around a lot and keeps cutting in and out. This can also be seen by probing the gate waveform. You can see here the duty cycle starts rising but then just starts glitching and pulsing. If we turn it back down to about 9 volts, you can see the duty cycle start to build and then go low again, but at this low voltage the pulses are wide enough to maintain operation for the amplifier. This amp uses the good old SG3525 IC to control the power supply, PWM, duty cycle, shutdown, protection modes, etc. As long as we have supply voltage on VCC and VC, 0 volts on ground, soft start is high and shutdown is low, this should produce reliable pulses. So let's have a look. VCC pin 15, stable. VC pin 13, stable. Shutdown pin 10, low. Now the soft start pin should start off low at 0 volts, and it has an internal pull up, so it should start to rise, and depending on the value of an external capacitor or other components externally will change the rate at which the soft start rises up to a higher voltage, therefore controlling the soft start function of this chip. So let's see what it's doing in our case. You can see here that it starts to rise but then keeps getting pulled back down to ground again, so this chip is in a forever resetting state of soft start. That means the output PWM on pin 11 and 14 is sporadic and glitchy and it won't power the amplifier up fully. So there's a couple of culprits here. Either the SG3525 itself is bad, or some of the components after the soft start pin externally on the circuit are going bad, therefore causing it to drag the soft start back down to ground again. So we can either start off by replacing the 3525 pretty quick and easy, or we can start by isolating or disconnecting the external circuitry on soft start to disable it and get the amplifier up and running just on the 3525 without a soft start feature. There's no obviously bad components in this area when I check them with the multimeter, so let's start by replacing the 3525 as a first best guess. Okay, let's see, has that helped? No. Now in order of likeliness for a component to randomly fail by itself, it tends to go in this order: semiconductor components, chips, diodes, transistors, MOSFETs, then followed by capacitors, and least likely is resistors. Now if I'm looking at what else connects to this soft start pin, we've got these 4148 diodes up here and down here, and because they are semiconductor components, they are more likely to have failed than anything else. Since the soft start pin has an internal pull-up, I thought I might as well power it up while the diodes are out to see what that looks like, see if it makes any difference. Unfortunately, it still glitches around like crazy, so the diodes aren't the issue here. The only other place this pin really connects to is through this 1K8 resistor through to this 072C. Now the supply voltages for this IC are generated by the power supply switching PWM, so it only really becomes active when the power supply builds. Now the power supply sections in these amps are regulated, which means that when the rail voltage reaches a certain threshold, the power supply will start reducing down the duty cycle, preventing the rail voltage from exceeding the limits of the rail capacitors and the output FETs. So somewhere around here there will be a circuit that listens to the rail voltage, and when it gets past a certain threshold, acts on one of the pins of the 3525 to reduce the duty cycle of the power supply. Aside from the soft start, there's another way that the PWM duty cycle can be changed on this chip, and that is with the compensation pin on pin 9. Pin 9 is the output of an error amplifier which sits on pins 1 and 2. You can see here we have a trace leading off pin 9 to this circuit, but also traces leading off 1 and 2 to this circuitry up here. You can see this on the block diagram. If the voltage on pin 1 is higher than the voltage on pin 2 of the comparator, then the output on pin 9 will go high, which will disable or reduce the duty cycle on the PWM side. Pin 2, which is the non-inverting input of the comparator, is connected to 5 volt ref, so the varying voltage which sets the comparator output is going to be on pin 1 with this circuit. You can see that pin 1 goes up here through this resistor to these diodes, but also goes down through this trace to God knows where. A schematic would be really handy right now. So pin 1 goes through this via and comes out here where we go through this resistor, and then that connects down here to the rail voltage. So it's basically just a simple voltage divider. If I bridge the output of the comparator pin 9 to 5 volt ref, we actually get good operation with full duty cycle being built and full operation of the amplifier that's stable. So we know that the issue must be in one of the external circuits that feeds the comparator. To try and narrow down which side is the issue, I'm going to first try lifting this resistor which goes to pin 1 of the comparator here, leading up to this top part of the circuit, and that should isolate it, and we can see what the behavior is then. Nope, okay, that hasn't helped at all. So next, let's lift this resistor that connects the rail voltage to the sense circuit. What are we saying now? Ah, that's better. So it possibly seems that too much voltage is getting through this resistor network from the rails to pin 1 of the 3525. If I briefly short out the inputs to the comparator here, which allows the rail voltage to climb way higher than it currently is without doing that, the amplifier remains in high voltage protect. It thinks the rail voltage is too high, but it's nowhere near high enough. It's only at 130 volts. And only when the rail voltage sinks back down again to under like 117 volts, like now, does it start trying to turn on again. So the fault is absolutely in the circuit that determines how high the rail voltage is, and it thinks it's way higher than it should be. I've just been measuring some resistor values, and this one, which is the last one in the chain that sends the rail voltage to the comparator, is supposed to be 210,000 ohms. However, it's actually reading 150 ohms. This is extremely rare. Resistors, when they die, they usually go open or higher resistance than they are originally. That's really unusual. But that being a low resistance than it should be will mean that more rail voltage goes through this voltage divider to the comparators. Now, I don't have that exact value, 210,000, but what I do have is I do have a 104 and a 124, which will get me to 220,000, which is close enough for a proof of concept fix. And if this works, then I will order the correct value resistor. So to series these together, I'm putting them on each one of the pads from the original resistor, and then I can just bridge the other two ends together with a bit of solder. Is it pretty? No, but as a proof of concept test, this is fine. So now let's have a look. Is the PWM stable? Oh, that's much better. Nice. And to show that we've got roughly the right value, if I now go up to 14 volts, this should start decreasing. Yes. Look at that. As we go now higher on the rail voltage, we get less duty cycle. Therefore, this is working as the regulated power supply is supposed to. And if we go down under 12 volts, we get full duty cycle. That is fantastic. That is a fix.